All right. Hey, Shani. Sorry you couldn't make it to our session today, but here is a video on one of the problems. All right. So hopefully you understand from here. I'm trying this for the first time actually, so let me know how it goes. So the problem that we have here is that a sample size of 49. So we have a sample size. So we have n essentially is 49. And then the sample mean we have is 35. So x bar is 35. And then the standard deviation is 14. All right, so that's the information that we know. And we want to construct a 98% confidence interval. And then we're given the z-value, so we don't have to look it up. There are standard values associated with each of these confidence intervals, so you might want to know what those are. For example, I believe for 95%, it's 1.96, I believe. For yeah, there's a bunch of different ones. 90%, I believe, is 1.645 or something like that. I don't remember, but you can just easily look this up in the just look it up in the web. But that's that. And so to construct a 95% confidence interval, what do we want to do? What we want to do is take that mean. So we have the mean, which is x bar, and then we're going to find two numbers. So it's essentially an interval, just like the name says. So we're going to have a lower end and then the upper end. So we're going to have two numbers. So what we're going to do to get there is we're going to take the mean, sample mean, and then add or subtract from that the product of the z-value that we know, which is given to you, 2.32 for 98% confidence interval, and then the standard deviation divided by square root of the sample size. Now, this is something that you want to keep in your toolbox, just like all the other formulas that I've given you. So make sure that you keep this in your toolbox. This is really critical for you to know. Because now you'll see in a second, this will give you the confidence interval for the problem that we have. Now, the sample mean that we have is 35. Let me change the color to something different. So let me just go with green. I've used green before, so I'm going to go with blue. All right, so we have 35. Oh, I forgot to change the color. I picked the color, but didn't change it. All right. Oh shit, this is really not working. Something's going on. All right, maybe this will be stable. Okay, all right. So we have x bar is 35 plus minus z-score that we have is 2.32 times the standard deviation that we have is 14 over the square root of n, which is the square root of 49. All right. With this, we will get to a point where we'll have an interval. All right, so let's get this going. So we have 35 plus minus 2.32 times 14 divided by square root of 49 is 7. And then, so we have, this is running a little bit slow, but hopefully it will all still do the job. So we have 35 plus minus 2.32 times 14 divided by 7 is 2. So we have 35 plus minus 4.64. So that with that we have the interval. But if you wanted to actually write it out what that looks like, we can just easily just subtract and add these two numbers. So we have the confidence interval of 35 plus 4.64 and then 35 minus 4.64. So the confidence interval for this sample mean, and I'll explain in a minute what it means, we have 39.64. So the upper bound for this is 39.64. And then what's 35 minus 4.64? That should be what, 30.36? 30.36. All right, I'm fairly confident in that answer. All right, so what this is essentially, right, and I'll write this out for you in a second as well. But what this does is we have a sample. So this is not, it's impossible in statistics really, I mean, unless if the population is really small, to capture every single observation in that population. What we need what we can do, what's feasible, is that we can go ahead and capture some sample of it, right? So in this case, we have a sample of 49 from a population. We don't know the population size. We don't know how big that population is, but we know that the sample size is 49. We know that the mean of that sample size, mean of those 49 numbers is 35, and we know the standard deviation is 14. What they're really asking us is, with this 98% confidence interval, is find a range that you can be 98% confident that the sample mean would be within that sample, right? Would be included in that sample, within that space, within that interval that we just calculated right here. All right. So with that, um, we have the interval. The way that you want to interpret, because it looks like we need to be able to interpret this, is we say, oh, let me go to the next page. Oh, no. All right, hopefully this will be stable. All right, so the way that you interpret the confidence interval is we say we can be whatever percentage. So in this case, we have 98%. 98% confident that the range, that our simple mean, that our population mean, or let me rewrite this. So we can be 98% confident that the population mean. So we don't know what the mean of the actual entire data would be, right? We just have a small sample of it, and then we know the sample mean is 35. We know that the sample mean is 35. But if we wanted to now know what would be a likely range where um, you can find the population mean, the mean of the entire data that we don't know. That's what the confidence interval is telling us. It's telling us we can be 98% certain that that the mean, the population mean, that the population mean would be within, can be 98% confident that the population mean is contained, oh, I hope that I spelled that correctly, contained in the interval that we just calculated, in the interval which is whatever we just calculated. So 39.64 and 30.36. 39.64 and 30.36. So the mean of this small sample that you calculated that we know is 35. But if you rerun this again, you would likely get a different, if you were to rerun this again, you'd likely be getting a different sample mean, right? Because it's impossible to get the same samples back, same samples back. But if you were to repeat this over and over every single time, the mean would be different. But we can be very confident with 98% certainty the actual sample mean is contained within this with 98% confidence. That's what it means, and you want to be very careful when you interpret it. The other way that you can say this, which I kind of actually hinted on, is to say if we were to, so that's one way to do it. If we were to, if we were to if we were to take 100 samples, so if you were to go back and take another sample, go back and take another sample, go back and take another sample 100 different times. If you were to take 100 different samples, 98% of the time, so 98% of the time, or or essentially in this case, because we're taking 100 samples, 98% of 900 of 100 is 98. So 98 times out of 100, you would get 900 times out of 100. The Okay, so if you were to take 100 different samples, 98% of the time, the population, this um, this interval that we have would capture the true population mean. So what that means is that, oh, sorry, I don't think you can see the whole of it. All right, so what that essentially means is that if you were to repeat this experiment over and over and over, right, like 100 different times, each time getting a different sample, you would have a different sample mean. But if you were to construct a 98% confidence interval, which would happen to be these two numbers, what you can say is that 98% of the time, or 98 different times out of 100 times that you sample, the actual true mean would be within the confidence interval that you just calculated right here. We'd missed it 2 times, so this is essentially what it means. 2 times out of 98 times, it would be somewhere else. Okay, so that is how you would interpret the confidence interval for this problem, or for any problem in general. And just a real quick recap, we have the sample mean right here. We have the sample size right here. We know the standard deviation as well, and we're to construct a 98% confidence interval, the z-value for which is also given to you. And so depending on this, though, so if you notice this formula really closely, how big of a confidence interval, so how big or wide the value that we calculated here, the interval that we calculated here, it would really depend on the confidence interval that you want, and then if you think about it, the sample size, right? So if this number is larger, you would, or this number is smaller. If this number is larger, you would have a larger confidence interval essentially. Or if this number, the n is smaller, you'd also have a smaller number, larger confidence interval. All right, so I don't want to confuse you with that, but maybe I'll make another video on that. But that's the gist of how you would do problem 1. All right.